not a chair.
Okay, so let's get started. It's 10 a.m. Europe time now. So welcome everyone to this hybrid IETF. So we will start with our share slides. So Jorge is helping us locally on site to manage the mic queue in case there are some comments. So thank you, Jorge, for doing that.
Sure.
This is our notewell. If you are not aware about it, please read it. Here is our agenda. So for this session, it's not fully packed. We have a couple of buffers available for discussion. However, we still need to have the presenters sticking on their time slot. Status update. So we have one RFC that has been published since last IETF, which is about the operational aspect for proxy RPND in Evpn environments. We have currently two documents as part of the RFC editor queue. So we have the Evpn bump procedure updates, and we have also the optimized ingress replication. We still have bunches of documents that are either under AD review or at the IESG. So I think the IGMP MLD proxy draft is quite close to the end, and the discussions are progressing well. And there are still a couple of documents that haven't been processed yet by the AD. We have currently 4 documents that are under Shepherd review. So on the Evpn unequal cost load balancing, we sent a request to IDR chairs a couple of months back, if I'm not mistaken, to get some review, especially because there was some discussion about this load balancing community and so on. So we really need to ensure that we agree on the solution. So it will be good to have the feedback from, or at least the agreement of IDR chairs on this one. Evpn FXC and MHPA, I have provided a review to the authors. I know that some documents have been updated, so I just need to read the updated version again to check that all the comments have been addressed. And I think, Matthew, correct me if I'm wrong, but Evpn LSP ping is almost ready to go.
Yeah, I gave that publication request last week. Okay. So thank you for everyone who worked on that.
We have currently two documents that are ready for working group last call. We have the Evpn redundant multicast source, and we have the BGP SD1 usage document from Linda as well. We have one working group last call which is still in progress, mainly because we are missing IPR poll replies. So this is for the Evpn FastDF recovery. So authors, please reply to the IPR poll so we can move forward with the draft. We did a last call for the Evpn multi-homing split horizon document. Again, on this one, we are still missing some IPR poll feedback from co-authors. So authors, please reply to the IPR poll. And there are also a couple of comments that have been provided by the working group and that authors need to address. So maybe Jorge, I think you are managing this document, correct?
Yeah. Should we publish a new version addressing the comments?
Yes, that will be good. So we can then move forward.
Okay, we'll do that. Thanks.
Okay, working group document update. So we will not go through all the draft. A few things that I wanted to highlight. So on the draft IETF BESS BGP multicast controller, there may be some overlap with some idea work on the P2MP segment routing policies. So we need to work with the IDR chairs and the co-authors of all drafts to see how we manage both documents. Evpn Geneva, I think we still wait for the authors to update the draft to be able to move the document forward. And what else? On the Evpn BFD, we are also still waiting for the authors to refresh the draft. So we are expecting to send the document to the BFD working group for a review, but we need the draft to be refreshed before we do that. I see a comment.
Yeah, there is a comment in the room.
Okay.
Sami?
Sami?
Yes, Sami, this is for the Evpn Geneva. I believe we updated the draft and uploaded the version 3. So was there other comments after that?
We can check again, but I think there was still some comments after the last version that has been published. So if you can cross-check on your side and confirm me that everything has been updated, then we can probably move forward. Okay?
Okay, so the comments will be on the list, right? Okay, I'll check
Yes,
the list.
you should be able to find them in the archive.
Okay, thank you.
We also have a bit of a dependency issue, I think, between this and the Geneva draft in Geneva VPN draft in MV03, which was kind of stalled due to lack of review.
Oh, okay. I saw Geneva already done, right? So it's not done yet in NVOC?
No, it's not done because we didn't get any comments on it. We need to get more review on it. It's very quiet over there.
Okay, thanks.
Geneva's done. Sorry, just to clarify, Geneva's done, but it's the applicability of EVPN to Geneva.
Ah, I see. Okay.
Okay. So we can probably move to the presentations. So I think, Jorge, you are the first presenter.
Yeah, I also had a question about the
Sure.
EVPN, IPVPN interworking draft. So the draft is going to expire soon, so we plan to refresh it and add some minor changes that we discussed among the authors. And once we do that, do we have any date in mind for that discussion with the ITR chairs happening, or?
I think the discussion already happened, but we are still waiting for feedback from the IDR chairs, unfortunately, for a long time.
Okay.
So I know that Sue already provided some comments, but I haven't really seen some reply from you, Jorge. But I think Jeff wanted also to have a look at the draft.
There was what I remember, there was an email from Sue. I replied with my comments, and that's all I remember.
Okay.
So there's a comment here from Kayur.
Yes, Kayur Patel, Arcus, and I'm one of the IDR chairs. So Stefan, I will make sure we will take it back to the IDR, and the chairs will, I will poke chairs and get you the feedback. Yeah.
Yeah, because there was a couple of really important points that we need to clarify in terms of process. Because the document, for instance, if I remember correctly, is defining for rules some rules about aggregation of some attributes and so on. But moving forward, we really need to ensure that we have the right process, because for each new attribute which is defined, there is a requirement to define what are the aggregation rules.
Noted. Thanks.
Okay. Any other comments on the chair slides before we move to the presentations? Okay.
Yep.
So Jorge, you can go ahead. Let me pop up your slides.
Okay. So good morning, everyone. My name is Jorge Rabadam. I'm presenting this draft about Evpn VPWS gateway solution on behalf of my authors. Next slide, please. So we're going to talk about three things here. So following pretty much the outline of the draft. So the first part is we'll talk a little bit about what Evpn VPWS interconnect is and why we are talking about service interworking or service gateway solution in this draft. Then we'll briefly talk about the extensions that we are defining in the draft. That's what we call the Evpn VPWS gateway procedures. And then next steps. Next slide, please. Yeah. So what are we talking about here? So this is a draft about how to interconnect Evpn VPWS services, or in other words, how to have an Evpn VPWS spanning multiple domains, where each domain can be an IGP instance or an autonomous system. And typically, this is for high scale, as I said, multi-domain networks. And each domain can actually have a different transport technology, MPLS, VXLAN, segment routing, V6, or segment routing MPLS. What we also want to do is optimize all the Evpn multi-homing procedures, including mass withdrawal. And if needed, we want to provide a solution able to provide translation of RDs, RTs, Ethernet tags, and layer 2 capabilities on the border routers. So looking at all the different options that we have for Evpn VPWS interdomain, in the draft, we classify the solutions in three groups. So the first group is what we call the service interworking solution or service gateway solution. The second group is what we call the interdomain option B solution. And the third one is what we call the transport interworking solution. So next slide, please. So the three solutions are illustrated here in this slide. So the first one is the service interworking solution. In the example, you have three domains and two border routers connecting those domains. So in this solution, basically, we instantiate a VPWS service on the border routers. The 80 per EVA route for the Evpn VPWS service is advertised from the egress P. It's imported and processed by the border router 2, and basically the route is redistributed into the domain 2 with the same or different RDs, and tags, and also encapsulation. Same thing would happen with border router 1. And obviously this is in one direction. The other direction, we will have a similar solution. So in the second group, or what we call the option B solution, there is no instantiation of the VPWS service on the border routers, but we have a typical model B on the border routers. And what that means is that the border routers will import the 80 per EVA routes, will program a swap operation on the labels, and they will re-advertise the routes with nextSwap self and also modifying the label. This would be the case, this is a typical case with MPLS, but that would be also the case if you have VXLAN, VNI, or even potentially a Service X as well. The third group is the one at the bottom, and what we call the transport interworking solution. In this case, you may notice that the route, the 80 per EVA route issued by the egress P goes all the way up to the ingress P. That route is not processed by the border routers. You can obviously have control plane route reflectors in between, but there is no inline route reflectors processing the routes or doing any swap operation with the labels. And in this case, if the domains, they have different encapsulations, like in the example, The only rule is that obviously, since there is no border router in the middle processing the route, the egress P and the ingress P, they must have the same encapsulation. Next slide, please. So in the draft, what we are doing is basically we describe the three groups, and what we are saying is that the three solutions are perfectly valid, but if you have the requirements that we represent here in the table, the service interworking solution is probably the ideal one. And those requirements are, for instance, if you want to have per domain Evpn multi-homing capabilities of per domain mass withdraw, or you want to provide the ability to translate RDs, RTs, tags, or L2 attributes, the service interworking would be the ideal solution. Also, this solution handles heterogeneous encapsulations in different domains, right? And you could even have Evpn level service OAM. Next slide, please. So based on that, basically we are extending the procedures in Evpn VPWS to handle this interdomain scenario. This is the service gateway concept is already defined in RFC 9014 for Evpn multipoint. This is pretty much extending the procedures for Evpn VPWS routes. And all the procedures in the draft, they refer to what we call redistribution. And redistribution here means all the procedures that involve three things. So the first thing is the reception and process of the Evpn route that is coming from the source domain. The second one is the programming of the forwarding path. And the third one is the re-advertisement of the route to a different domain, which is what we call the next destination domain. So for the first one, the reception and process of the routes, basically we follow the RFC 8214. And we extend that with the DPath that we use in this type of scenarios for loop prevention and also for best path selection. The forwarding state programming is basically we receive a route, we program the received label or VNI or SID. We allocate a new label VNI or SID, and we re-advertise that, and we program this switching operation between the two. And the third part is the re-advertisement of the routes. So in the draft, there are certain rules that you need to comply with. Usually you will, when you re-advertise, you use different route distinguishers to provide enough diversity within the domain. You can use the same or different route targets and ether tags. We use ESI 0 unless you define an interconnect Ethernet segment, as we will see in the next slide. You can regenerate the layer 2 attributes, which includes the control word, signaling, the flow label, and also the MTU. The P and the B flags that we use for multi-homing are not propagated, but they are regenerated based on the interconnect Ethernet segment state. And we also describe some other rules like the propagation of communities and also how you update the DPath attribute. Next slide, please. So for redundancy of the service gateway, there are two solutions described in the draft. Solution number one is called Anycast Gateways, and it's a very simple solution. So here the idea is when we receive the routes from the egress P, in this example in domain 3, that route is imported by the border routers or those service gateways, 21 and 22, and they are redistributed into the domain 2 with the same Ethernet tag identifier. So the border routers 11 and I should say 12 at the bottom. Basically, they do best path selection and they pick up one of the two, and they re-advertise or redistribute the route into domain 1 with the same Ethernet tag as well. So this is a very simple solution. There are no Ethernet segments I configured here or created, but basically we provide a path based on best path selection. There is no on a per flow basis load balancing or anything like that. The other solution, which is a bit more sophisticated, is what we call the EVPN full EVPN multi-homing with the interconnect Ethernet segment. The interconnect Ethernet segment is something that we defined in the RFC 9014, only now extended for EVPN VPWS. And this is a full Ethernet segment construct. So basically, you can define all active or single active multi-homing. You have properties like mask withdraw, aliasing, backup, and it's all happening within the context of the domain. So the AD per ES routes are not propagated; they are consumed within the domain by the service gateways. So, and this is the more powerful solution, providing on a per flow load balancing if you want it for all active. Next slide, please. So next steps for this draft is basically we are seeking for feedback from the working group, and yeah, we wanted to hear if this is useful, and eventually we'll request a working group adoption. Any comments or questions? Yeah, there's a comment here in the room.
Yes, hi, Himanshu from Siena. Is this the service gateways based on the VPWS L2 VPN pseudowire switching type, almost the same concepts, right?
It's a service gateway solution for EVPN VPWS. Yeah.
Why not call it that way?
It's called EVPN VPWS gateway. Yeah.
Yeah, because I think in the past when I was doing something and I called service interworking, I got a lot of pushback from the group that you cannot define, you cannot do service interworking in the IETF. In those days, it was like ATM frame relay type of thing, and IP service interworking was not something that is standard for IETF. So I had to change my drafts and all that other stuff.
Yeah, but I don't understand the question in the sense that this is pure.
So
it's full EVPN VPWS end to end, right? So the.
It is, and it is. I think I feel this is similar to the pseudowire switching and multi-segment pseudowire, right? The maybe you want to change the. I mean, it's up to you, but the service interworking aspects is problematic for IETF. In the past, I don't know. Maybe things have changed now.
Okay, so you're saying the service interworking term means something else that in the past created some confusion?
Yeah.
Yeah.
But
I mean, we can change the terminology. Yeah.
But we already did service interworking, for instance, between EVPN and IPVPN, so I don't really see what is the issue here.
I think that the issue is that there are different services. Service interworking is matching typically one service to another service, whereas this is doing, this is kind of slightly different because it is still EVPN end to end.
Yeah.
right. Exactly.
It is EVPN end to end. Yes.
That exactly.
Okay. Okay, let's move to the other question. Loa, you had a question? Go ahead, Loa.
Hi, Loa. When I was looking by another name, when I read the slides, I saw the slide that you have on top now, and that is requesting feedback, so I didn't bother that much. But now I kind of heard you saying that it's almost ready for working group adoption. I think you should hold this off a bit, just because it was listed as an other document.
Sorry, it was hard for me to understand. The comment is.
The comment is that on the agenda,
Yeah.
this document has another name.
Sure.
So there are quite a number of people that hasn't been able to prepare the meeting. And if you're only requesting more feedback, I think it's fine. But if you're saying that this is ready for working group adoption, then I think you should hold that off a bit and allow us to actually read the document with the new file name.
Sure. And my apologies again because we changed the name of the draft at the very last minute before posting the draft, and I forgot to update the chairs, so that's why it was not the right name on the agenda. And we're not requesting for working group adoption yet. I mean, this is draft 00, so for the moment it's just feedback. I said that eventually we will request working group adoption, but not at this stage. So absolutely.
Okay, that's fine. Thank you.
People will have time to review, of course.
Okay, Jeffrey, really quickly.
Very quickly, Jeffrey Haas. So I noticed that you're doing the route distinguisher rewrite. This is often a problem because it causes routes to potentially replay themselves across domains. Is this procedure done anywhere else in best documents?
Again, sorry, it's hard for me to catch it. So the question is whether this is for L2 services?
The question is route distinguisher rewrites.
Oh,
do any other best documents do it?
I mean, what we are saying here is that we recommend the route distinguisher rewrite, okay. Because that is giving you path diversity across domains, right?
It's problematic. We will send mail.
Okay, then we should discuss in the list.
Okay. Okay, let's move to the other presentation. I think you, Jorge, about the draft.
Yeah, okay. This draft was already presented last IETF, is revision 01. It's called the domain path for Ethernet Evpn. So we'll talk about a short refresh, what's new in the draft, the next steps. So next slide, please. Yeah, domain path is defined in this Evpn IPVPN interworking draft. And that draft is used for layer 3 routes, meaning IPVPN, PEC, BGP routes, and for EVPN routes type 5 and routes type 2 in the symmetric IRB model. And this draft is basically modified by service gateways along the way, and is used for control plane loop protection and best path selection. There are some procedures related to it. So next slide. So in this draft, basically, what we are doing is extending the use of the path also for EVPN routes that are not used for layer 3, but also for the rest of the capabilities. So, and just like in the EVPN, IPVPN interworking draft, this is used for loop protection on the gateways, and also provides traceability and best path selection on the receiving piece. Next slide, please. So what is new in this revision? So there are new authors added, Malika, Patrice, and Wen, and their contributions are now incorporated to the draft. So you will notice section 1 has changed. Now it includes the use cases that are justifying the use of DPath in these environments. We clarified the terminology, we did a general cleanup, and also we are making some changes in the specification itself, which is in section 4. In particular, we now allow the DPath to be used also for IMET routes or EVPN routes type 3. And as such, we are also explaining why we are using DPath for IMET routes. We are also including some modification of the use of DPath for MAC IP routes. Next slide, please. So in particular for the MAC IP advertisement routes, if you are in an RFC 9014 gateway type of scenario, the DPath is used. If you look at the left-hand side of your slide, P1 advertises a MAC IP route that is imported by the gateways, gateway 1 and 2. So for instance, when gateway 2 re-advertises that route into domain 2, it basically slaps the dpath with the domain 1 identifier that is received by gateway 1 and identified as a looped route. So what we are doing in this revision is we allow to actually install that looped route as long as there are no other routes available in the router. A typical example would be what you have on the right-hand side of the slide in the diagram. So if gateway 1 loses its peer to the route reflector in domain 1, for instance, obviously the MAC IP route received directly from P1 is actually lost. And in that case, the route that it received from gateway 2 can be installed. And in this case, is used for fast convergence, for in-flight packets, and it can help in that sense. So that's why we included this case. Next slide. So we identified also some cases where the two gateways that are stitching domain 1 to domain 2. They advertise in RFC 9014, they advertise IMET routes for the two domains, and we want to avoid parallel EVPN paths for bump traffic between the two, in case you have local attachment circuits on the two gateways. And one way to differentiate those routes and pick up only one and have only one bump path is to actually use dpath, right? If we add dpath with a local domain to the gateways on the IMET routes that are advertised for domain 2, we can identify those and not install those, and we only install the ones for domain 1. Next slide, please. So next steps. So there is a section in the draft that talks about best path selection for the EVPN routes. But we basically discussed, and we think that section should be clarified in the RFC 7432-BESS draft. And this document should just refer to that section and modify that section with the new addition of the dpath for the EVPN routes. So we'll make those changes, and we'll synchronize those changes with the RFC 7432-BESS draft. And after that, we want to receive more feedback from the working group. And after that, the draft, we think, will be ready for working group adoption. And that's it. Any comments?
Any comments? No comment. So I think we can move to the next presentation.
Okay, this one is a short update. So it's the IP aliasing draft version 04. Next slide, please. So changes in revision 4, there's a new co-author, Lucas, based on the use cases that he brought up for the draft. And actually we included one of those use cases that we call centralized routing model. Other minor changes, general cleanup, typo fixing, and references updated. Next slide, please. Yeah, so this centralized routing model is described now in the draft. Basically, what this is about is if you have this an environment where you use the IP aliasing procedures or these layer 3 Ethernet segments, what we want is, in some cases, we have some CNFs or VNFs and that are attached to the EVPN layer 3 network. And those CNFs or VNFs, we want to simplify the configuration and the operation. So they basically, instead of having a direct eBGP PEC session to the directly connected leaf, what we want is to have a peer to a centralized leaf. In this diagram, we call it PEC, as in centralized. And all the CNFs and VNFs will have this BGP session to the centralized leaf, right? So in this diagram, we are only illustrating the procedures for one of them. You see the CNF has an eBGP PEC session to PEC, to a loopback in the IP verb. And through that session is advertising, for instance, a subnet 50.0/24 with next hop 10.1, which is the IP of the CNF. The centralized leaf basically imports that route and is going to re-advertise a route type 5 with the next hop PEC, and that will be imported by the rest of the leaves attached to the IP version. So if we didn't do anything special, the traffic coming from H4 to a host in that subnet basically would trombone through PEC and then to the directly attached leaves, P1 or P2. So what we want here is to avoid that tromboning, and that is what this layer 3 Ethernet segments provide. So we define this new Ethernet segment construct on P1, P2, and PEC. However, PEC will not advertise the 80 per EVA routes because the CNF loopback is not known through a non-Evpn route. But PE1 and PE2 will advertise the 80 per EVA routes. So PE3 actually resolves the prefix to the owners of the 80 per EVA routes and can do load balancing to PE1 and PE2 and not send the traffic to PEC. So that is the use case that we introduced. Next slide, please. And basically, yeah, we've been presenting this draft for a while, so we really think it's a very useful draft with use cases and implementation, so we really want to ask for working group adoption.
Any comment? Okay, there's no one in the queue.
Okay. Thank you.
Thank you. Okay. Next speaker is Soumya.
Yeah, hi everyone.
Yep, you can go ahead.
Yeah, sure. My name is Soumya, and me and Vinayak have put down this draft few months back, and we are not able to present it in the last IETF forum. Can you move to the next slide, please? So this is regarding a use case which we have encountered in one of our. We came across this use case in one of our customers' deployments. So we thought of taking this up in the BESS forum before writing this together, putting up this together. And there were few discussions where few of the BESS members have responded back that this is more of implementation requisite, but we thought it was otherwise. We can solve it in a generic way via a control plane based solution. So that's where we are. So the agenda here is again the introduction, the problem statement, and the use case, which is tied to it, the solution, and then how this control plane extension is backward compatible or otherwise. Please, next slide. So next slide, please. Essentially, this was a case of active firewall deployment, wherein you have the same physical device with a virtual credential, and it's placed on the same Ethernet segment, but in, let's say, a different fabric, which is connected over WAN, or let's say over a DCI. It can be a typical NVO fabric, which I don't want to use the word NVO, but just for an overlay reference, which can be deployed via Evpn control plane or supported via Evpn control plane. That's the reason I mentioned it here. So it's about the active firewalls where two instances of the same firewall which are carrying the same virtual credentials are active instances, but they serve their local site. They don't talk to each other per se, or we would want it to be not as in a load balance kind of dealing. It has to be preferred in such a way where the local deployment serves the requisite. Next slide, please. This is what I was referring to, where the bricks are the firewalls, and assume that these are two EVPN based fabrics, one on the left, another on the right, site 1 and site 2. And the firewalls here, which are hooked to which are also hosting the gateways, are hosted by the border leaf. Uh, just a sample topology. It can definitely differ from this one. So essentially, all the local hosts on the site should be targeting their packets or any control plane requisite like ARP response and request for the gateway should be redirected towards the local firewall. And any bum traffic per se, including the ARP request, should be dealt locally by both the firewalls, by both the border VTEPs, which are stationed across two different sites and part of the same EVPN extension network, right? So yeah, so this is both firewalls are hooked to the same Ethernet segment, though carrying the same credentials, same virtual MAC IP, for an example, and but they are two separate physical devices per se, which may or may not have an orthogonal way of talking to each other, to maintaining states. That's oblivious here. And the red lines show the typical flow of data traffic within the site. Next slide, please. Yeah, I
Soumya,
think.
Soumya, you have to speed up a bit if you want to be able to cover your second draft.
Sure. So we can skip this one. I think this I've already covered. Probably I should have. Yeah. So the requisite here is that both the border leaves or both the VTEPs here or should act as a designated forwarder. Both can flood the traffic. Both should be able to flood the traffic at the same time. So it's about supporting more than one designated forwarder for the same Ethernet segment and BD combination, right? So that's the idea here, and that's what we are proposing here, that we want to have a new mode of selection for DF, which is equivalent to having all PEs in scenarios like this, all PEs which can act as a DF. And yeah, so that's what the uh, request here is. Yeah, we can move to the next one. So the send side and receive side are, I mean, again, we support the new DF bit, new DF value, just an increment to the existing ones. We have 0 and 1 right now being supported for default, and uh, one which was extended in and extended by RFC 858/74/7432. So if at all we have, I mean, we can choose the available next value, and the tentative proposal is to use the next value, which is 2. Again, to be backward compatible, if any of the routers which doesn't publishes a non-2 value, or it doesn't supports this extended community, the default falls back to the to RFC 7432, the default selection. Receive side processing is again the same. So send side and receive side is mostly about being backward compatible or being able to revert back to defaults if one of the P's don't publishes the all P's DF mode. So yeah. Next one, please. I think yeah, same thing, and the last slide. This can be skipped. Yeah. Yeah, so I think this is what we expect, more discussion. I shouldn't say working group draft, but more discussion and feedback on this proposal, on this draft, or if there are any existing ways which are already providing these enablers, definitely we want to collaborate. Work.
Okay, so we will take questions However, Sonia, you have used the time for your draft. So what I propose is, if we have time at the end of the meeting, we will do the presentation of the second draft. Okay?
Okay.
Jorge, you are on the queue.
Yeah, I have a couple of questions. So thanks for this presentation. So the first one is you are requesting code point 2 for the DF algorithm for the DF election extended community. That is actually the one we use for the preference-based DF election. So hopefully you can actually remove it from the draft as soon as you can, please. And the second one is, since you are asking for any other way of doing this, so in 7432-BESS we have this default gateway extended community that is already specified, that can be used with MAC IP routes, and actually it indicates that the route is being advertised for a kind of a default gateway, which is what I understood in your use case you want to achieve. And it's already specified that this extended community is not going to be subject to mobility and things like that. So the only difference with your draft or your use case is that in 7432-BESS that is used for IRB MAC IP routes. In your case, it wouldn't be an IRB, but it would be something attached to an attachment circuit. But I don't see why you wouldn't use that instead of an Ethernet segment. To me, an Ethernet segment here in this use case is kind of a strange thing to use. But we can discuss more on the mailing list.
Sure. Okay. Yeah.
Okay. Linda?
Okay. I have a question about the use case. Can you go to a few slides earlier? So you have a firewall on both sides, but each side you only have one firewall, right? I'm a little confused, like why you need to talk about multiple default firewalls. So all the traffic
Yeah.
from side one goes through that same firewall, right? So it's really just one. It's a little confusing on your graph.
Yeah, essentially there is one, but we don't want the tromboning of traffic when, let's say, site one based hosts are sending traffic north-south to the outside world. It should not get tromboned to the remote site's firewall instance, right? It should only be routed to the local one. Yeah, I understand. Typically, you would have different credentials, but this is one specific case where we want to have same virtual credential for both the cases, for both the sites. And in case the local one fails, that's the time when the bump traffic or north-south traffic should be tromboning to the remote side as a failover addresser.
Okay. Thank
Yeah.
you.
Okay. So let's move to the other speaker, Aibo.
Hello, this is Haibo Wang. There is our presentation. Now we are introduce the advertising SPFP neighbors in DTP. Okay, next slide, please. This is this simulation. We are update some general description based on the real comments. The meeting, Greg send us many comments, and I will update it. Next slide, please. This is our motivation. SPFP is very useful for 3G terminals. It can save resources for one side.
Your voice is breaking a lot, Aibo. I don't know if it's just for me, but we cannot hear you anymore.
Stefan, it's not just you. No, neither.
Aibo, can you hear us? Okay, so what we could do is probably to move to the next speaker until Aibo is able to sort his audio issue here. Okay, so we'll come back to this presentation later. So next speaker will be Gian.
Yes. Hi, my name is Gian Mishra. I'm with Verizon, and I am giving an update to the IPv6 OLEP design, as well as providing an introduction to a new draft IPv6 OLEP design, all SAPI. So this first draft IPv6 OLEP design, it was adopted last year on the 28th. So with this draft, one update that we have to the draft is we initially the draft was we were in scope was testing for this VCP was the PEC edge scenario. So we added inter-AS scenario to that. That was in the original draft, and we had removed it, but now we're adding that test back, I guess, into the draft. So that's testing both SAFI 128, so VPN and MVPN into the draft. The new draft, so this draft is a BCP draft. So this next draft that we're introducing, that I've been providing an introduction for on this call is it's called IPv6 only P design, all SAPI. This one is standards track, and this is a superset of the original draft, the IPv6 only P design. The difference between this draft, so this is what I call the design draft, and related to the original draft. The original BCP draft is testing with the 5 different vendors: Cisco, Juniper, Arista, Nokia, and Huawei. And this draft is providing the design framework. With this draft, the focus is and how it's different is it focuses on all SAFIs. So not only the AFI SAFI that are being tested in the original draft, but all other SAFI. Next slide. Next slide. Thanks. So here, what I've done is I actually kind of broke from the IANA page for AFI SAFI. What I did was I took all the FSAFI, kind of broke them up into functional groupings. So the first case, functional case of AFI SAFI is an edge customer NLRI, IPv4 and IPv6 NLRI, and that's a unicast SAFI and multicast SAFI. The unicast SAFI is one of the SAFIs that we're testing in the original draft IPv6 only P design. The inter-AS AFI SAFI is the additional one that we are testing. So that's SAFI 128 for VPN and 129 for MVPN. We're also testing as well BGP labeled unicast for 6PE and 4PE. So in addition to those SAFIs that are in the original draft, so the second functional area is inter-AS, ASBR to ASBR inter-AS peering. So in there we have 1/40 VPN auto discovery. The next category is multicast, and there we have VPN, VPL, MCAS, VPLS, MDT SAFI, multicast tree. And the next category is any peering that's going to a controller, so an SDN controller. So that would cover like BGPLS or a routing SAFI, routing policy SAFI, or the BGPLS SPF. And the next category is L2VPN. The one after that is optimizations, and then the last category is any kind of routing policy. Next slide. Next slide. Thanks. So here what I did was I had, this is the link, just the IANA API-SAPI link that has all the API-SAPIs, and I have it color-coded into functionals. Next slide. Next slide, sorry. And then here as well. So basically, what I'm showing here is just color coding, of all the functional, basically the IPv6 only P design, all SAPI. All of the address families and subsequent address families are supported. I did highlight in yellow the SAPI 76. On the previous slide, I had forgot to highlight SAPI 4, which is BGPLU for the transport. So the transport SAPI would be something, that's the transport layer. And what this draft is primarily concerned all SAPI related to the service SAPIs and not the transport SAPI. Next slide. Next. So here I'm showing just a dual stack scenario. So this is a typical, a PEC. You have two separate peers. A traditional dual stack. Next slide. And then here we have a single peer, and we're carrying both the V4 and V6 Nlri with a single peer. Next slide. Okay, so here this is one of the scenarios we are testing in the original IPv6 only P design draft, so that we've added SAPI 128 and SAPI 129 MBPN. So this is separate peers. Next slide. And here we have it combined into a single peer group. So both SAPI 128 and 129 are carried, using a single peer. So eliminating any V4 peering, and this is where IXP pops or any edge peering we actually can save, as well as inter-AS peering at IXP pops. Next slide. And so this slide is showing kind of the framework of the all SAPI, so other additional SAPI. So here we're showing SAPI 128. We're showing MCAS 3 for this. So this is a this is a new draft, I think, with BGP SAPI or stateless multicast, and then SRTE. So instead, so here we have two separate peers carrying the SAPI. Next slide. And then here we're actually just a single V6 peer, and then here you can see we're carrying all three SAPIs with a single peer. Just showing the framework of how this draft, this new all SAPI, it applies to all address units. All SAPI, subsequent address units. Next slide. And this slide shows a controller scenario. So you have a PE peering to a PC or SDN controller, and here we have BGPLS, and then routing policy SAPI, RPD SAPI, and here we have two separate peers. This is traditional dual stack. Next slide. And here we have a single peer. So we can see the savings. You really are able to eliminate the V4 peer, and you're able to carry, just showing a variety of scenarios where instead of having separate peers for V4 and V6, now it's really any SAPI, any of those IANA SAPI sharing the list that are, that are defined. They can all be carried, with a single V6 peer. Next slide. So as far as updates for the IPv6 only P design draft, here's the list of the hardware platforms and code that we're testing with Cisco, Juniper, Nokia, Arista, and Huawei. Next slide. This is our test plan that we have. So we have the core. We're using ISIS as the underlay, VCMP. We're testing really the main things that we need to test, I think, related to functionally testing and ensuring that everything works with the IPv6 only P design. We're testing BGP pick, next up self, label allocation mode per CE per VRF, route reflector function, add path, next up and change, P link and node failure, and then edge scenarios. We're testing BFD, lag, IPfix, QoS, and then CE link and node failures. Next slide.
Gian, you have to conclude. You have less than 1 minute.
Okay, thank you. So let's go to the next slide. Next slide. So this is the inner AS our architecture that we have set up in the lab with each of the vendors. What we've added in here is the inner AS. So we have two paths between the ASs, the AS on the left and the AS on the right, to test. So now we're able to test both the edge scenario and then as well as the intra AS scenario. Next slide. So here we've added in basically SAFI 128 and 129. So this lists all the different tests. It's a total of 12 different test scenarios that we will be testing. Next slide. Right, this is the last slide. So we made some significant progress with Juniper in testing, and with the testing, we've been able to successfully test the PEC edge scenario where we have an IPv4 and IPv6 Nlri. From a control plane perspective, they're being carried over a single v6 only peer, and we're forwarding v4 and v6, and we have end-to-end reachability CE to CE, and we're using the default per CE label allocation mode. We've tested with a v4 only core. We've also tested with a v6 only core. And we proved that the solution works. So everything's so far so good. We haven't seen any issues, and the testing is basically we're trying to prove out that what you would normally do with the dual stacking, we're able to do with a single V6 peer and provide the same identical functionality as dual stack. Thank you.
Okay. Unfortunately, we don't have time for questions. So if people have some questions, please raise them to the list.
Thank you.
And thank you again. Next speaker will be Keyo.
They will do it.
All right. Super. Hey folks, my name is Kevir Patel, and I'm going to talk about the MUP SAFI mobile user plane SAFI draft for BGP. This is a draft that I've co-authored with Tetsuya Murakami, Satoru Matsushima, Jeffrey Zhang, and Sudesh. Next slide, please. Following are the contributors who have contributed significantly to the draft. Next slide, please. So here is the motivation. There is a SRv6 MUP architecture, MUP stands for Mobile User Plane, draft that is presented in DMM working group, and it defines SRv6 based mobile user plane architecture for distributed mobility management. Basically, this architecture integrates mobile user plane into SRv6, and the way it does that is that it transforms session information from mobility management system into necessary routing information, but with SRv6 as a forwarding fabric, one forwarding fabric. As part of this architecture, it also defines the following things. It defines a notion of mobile user plane router or a PE router and a controller. Two new segment types are defined, SRv6 segment types for the MUP segments. It's called direct or interwork segment. And then there are two new session transform routes that are defined. And these are the routes that controllers would announce. The MUP segments would pretty much reside on PE. Next slide, please. Now, it also defines two new well-known routing instances akin to very similar to VRFs. It's called interwork segment for N3 RAN. This is the segment that allows you to connect N3 interfaces between G node Bs and UPFs, and a direct segment N6DN which is an N6 interface between UPF and data networks. Again, you should think of these segments connecting into a layer 3 VRF-like routing instances. And with that being said, what this draft does is that it defines a new BGP SAFI that allows this MUP extensions to work with BGP as a control plane. Also adds a new extended community as part of defining a new SAFI. Yeah, next slide, please. So this is how the Nlri format looks like. It has an architecture type, which is 1 octet, followed by route type, length, and then route type specific fields. The architecture type defined in this draft is 3GPP 5G. Subsequent drafts can define newer architecture types, but for now, for this draft, it is 3GPP 5G. Next slide, please. So as part of this architecture type, there are 4 new route types that are defined specifically for this architecture. 2 of them are discovery routes for different segments that we have defined, and 2 of them are session transport routes that carries routing information. 2 discovery routes are interwork segment discovery and direct segment discovery routes. Now, the route types could be shared across different architecture types as and when they get defined, but for this architecture type, there are only 4 route types that are defined. Next slide, please. So a little bit about, again, the well-known routing instances that are being defined. You have N3 RAN as a routing instance, and N6DN routing instance. And then you have discovery route, interwork discovery route that connects with N3 RAN routing instances. So anytime you have N3 RAN VRF-like routing instance on a PE, you would announce interwork segment discovery routes. Anytime you have an N6DN routing instance, you would announce direct segment discovery routes. The kind of stuff it carries within the route is prefixes for gnode Bs, prefix SID attributes, PE locator followed by GTP 46E function. And when you look at N6DN, it carries MUP segment, same prefix SID attribute with PE locator followed by n.dt46 function or dx base function. Next slide, please. All right, so 2 new route types, a little bit about them. Type 1 route carries end user reachability information. It carries tunnel endpoints, GTP, TEID, QFI. All these things where you talk about TEID, QFI, and the tunnel endpoint, they are architecture specific, 3GPP, 5G specific, and therefore the Nlri has an architecture specific field in which it's been carried. Now, these route types are announced by controllers while the discovery routes were announced by PEs. So tunnel endpoint that is announced by controller, it's been resolved using interwork segment discovery route, which also carries the locator and prefix ID. So you would have this route recurse over the tunnel endpoint route and resolve that. When it comes to creating forwarding SID for GTP46E, it is basically generated using the procedures mentioned in SRv6 mobile uplane draft. Yeah, next slide, please. And I think this is my last slide, but the type 2 session transform route again is used by N3 RAN routing interface. It carries UPF addresses. The TEID again that it carries is very specific to 3GPP 5G, and it's carried in appropriate field in Nlri. This route type also carries MUP extended community, and it carries the direct segment information. On a PE, there could be a multiple N3 RAN routing instances. What this direct segment information allows you is to map a appropriate segment for a routing instance that is present on a MUP, on a PE, and it lets you simply forward the traffic to that basically a routing instance. Now, all of these are carried with route target extended communities, import route target extended communities, and so the appropriate filtering would be done in a manner such that only the necessary routing information stays on a PE, on a given PE. Yeah. This is, I believe, my next slide. Yeah, this is my last slide. The draft is in fairly good shape. Version 1 of the draft will be submitted soon. We would really like to get a working group feedback, and once we've submitted a version 1, we'd like to have a working group consider adopting this draft. I'll be open for any questions that you may have.
Linda?
Question about this N3 RAN versus N6 RAN. Are they in one domain, segment routing domain, or separate?
They are separate domains. You want to think of them as they are two separate VRF-like instances that are configured on a router. Think of it as a provider edge routers. And in that sense, they are two separate domains.
So because they use different address space, right? In N3 RAN, the address space is GNOB and UPF. That's the address because in between them, they have GTP tunnels. And then after with N6, that's the client route. So they're very complete different. So how do you merge them together?
There is an architecture draft that talks about it very nicely. I can forward that to the working group as well, but it defines the rule sets to say how the routing information is stitched across different VRFs as and when, or different routing instances as and when you want to forward the traffic towards, yeah?
Okay, thank you. That's in the DNN document?
Yes, yes,
Okay.
SRv6 map architecture.
Okay.
Thank you.
There is a question here in the room.
Yeah, Loay Jalil, is this SRv6 specific only?
It starts with SRv6 as a specific forwarding plane, but the BGP procedures are universal and can be applied to the MPLS. There is an MPLS draft also as a forwarding plane that comes through.
Wim?
Wim Hendricks, Nokia. My question is, what is the goal of this draft, and is 3GPP somehow going to adopt this? Because today they
Can you speak a little louder? I'm so sorry.
My question is, what is the goal of this draft, given that 3GPP owns the architecture of 5G? Typically, are they trying to incorporate this architecture in their specification?
No, because I haven't, as part of defining this draft, I haven't done any modifications through 3GPP. What we have done is universally define BGP as a mechanism to build a fabric or a control plane in a manner that the packets would be carried from RAN into the data networks. So I believe this is a standalone draft. It has VPN-like semantics. That is one of the reasons I have brought it to BESS, because BESS deals with services.
But so you're only, I haven't read into all the details, you're only discussing the connectivity between the radio and the UPF, and then UPF, and then, but not so you're not trying to replace the signaling of GTP that they are using between the radio and the UPF? Okay.
Not replacing the signaling, but can be encompassing the signaling from GTP to SRv6, which is defined in the architecture draft. But this draft relies on the procedures that are defined in the architecture draft to do an appropriate conversion. Here we have defined BGP as a fabric that makes sure how does it work and interwork between the RANs as well as the DNs, that is the data networks.
Okay. Gian, you have a question?
Sure. Peter, I was wondering, with 3GPP, has there been like maybe a gap analysis or problem statement of what was in the existing 3GPP architecture? What gap existed, or was it actually mainly IETF technologies and new technologies, let's say like network slicing and SRv6 or whatnot, that has actually driven the development of this new solution, I guess?
So again, thank you for the question. Again, I thought I described it well in the motivations part of the draft early on. The motivations are that there is no BGP-based mechanism or a fabric that can achieve this. The draft's goal is to use BGP as a fabric to build where you can translate a SRv6 to GTP, and that is the motivation. One of the reasons, again, I will repeat, but I will be quick, is that bringing it to BESS, because it has a VPN semantics, it has a services like semantics, it's a great place to bring it in. That's one of the reasons why we presented it here. And I think it belongs here.
Thank you.
Okay.
Thank you.
Thank you,
so
Keyur.
much.
Next speaker is Mahesh.
All right, this is Mahesh Jetanandani, and I'm going to talk about the SRv6 MAP-YANG model. You got the introduction from KU, and I did post this draft actually this morning into the BESS working group. Sorry for that confusion. I should have done it before the cutoff, but we posted it to the wrong working group. Next slide, please. All right, so as KU talked about, his draft, this particular Yang model is talking about the configuration aspect of BGP, and I'll come to that in a minute, for the mobile user plane. Again, it aligns with the SRv6 MAP architecture draft being discussed in the DMM working group, which basically integrates the mobile sessions, as KU talked about, into IP information. And it uses SRv6 to specify the source routes to and from the mobile node. The architecture draft does recommend the use of BGP, and therefore we have used BGP in this particular Yang model. And as KU mentioned, there's a new SAFI that he has introduced as part of that draft, which is what we are going to use in this particular Yang model also. Next slide, please. So let's talk a little bit about what is the actual model doing. It's augmenting the current existing BGP Yang model in the IDEA working group. And it adds SRv6 particular node at a global level. And inside that particular container or node, we all add the MUP capability for both uplink and downlink configuration. In addition to the base BGP Yang model, it also augments the BGP policy model for a defined set, in this particular case an interface set, and it adds both a match and a set options. I'm not bringing up the tree diagram here. I think that would be better served by reading the draft or the Yang model tree itself. Next slide, please. Right, so essentially we have gone through one cut of the Yang model, and we made sure that it validates, it compiles. But we do expect a revision, not only of the model, but also of the draft. And in particular, we're going to focus on an example for how it could be used for configuration. We'll be updating the security consideration section for the draft. And this is a question to the working group as feedback is what operational data would they like to see being modeled as part of the model. And I think that's pretty much my last slide. Any questions?
We don't have any questions.
Right. Thank you.
Thank you, Mahesh. Next speaker is Heng. I need to check where are your slides. Okay, yeah. Okay, you can go ahead. Heng, we can't hear you. could you send me a message if you are able to hear us? Because we are not able to hear you. You may have to fix your audio. Okay. So we are not able to get you. So we will move in the meantime to the next speaker, who is Pascal. Pascal, do you want to take over with your presentation?
Yes.
Let me just open your slide.
Also, your you will be doing slide. Okay. Okay. So really the context of this is kind of interesting at this moment because there is more again a bit discussion on the Nlri database about IPv6 and whether the service providers like it or not. And if you look at the bottom line of those discussions, it's always something like IPv6 is giving us a lot of hassle because we have no control on the address. We have no control on who is who. And that really boils down to neighbor discovery and the way addresses are formed with auto configuration. And so, if you can go to the next slide, please. Yeah, compared to IPv4, which are what everybody operates, IPv6 is different. It's very clear. It has very observable difference, which impact the way the network can be operated. With V4, we had DHCP, one address per node. The DHCP flow was observable. You could see the request coming in and the response coming back. You could snoop for it and know which MAC address. Basically, that's what the service providers many use. Or with V6, the DUID, but basically who owns which IP address, and usually there was one IP address per node. So that made the network side of the operation kind of simple and deterministic. And another thing which comes with DHCP is the fact that for each address that's being formed on the network, given to a device, you could say how long at most it's going to stay on the network. So either it's refreshed or it's gone. Next slide, please. And with V6, and more specifically with stateless address configuration, all this is gone. It's basically the concept that a node can form any address and as many addresses as it likes, without really asking the network if it can do that, and without really telling the network how long it's going to use that address, when the address can be deprecated if there is any state in the network associated to that address. So it's all linked to the fact that the expectation is the network has a cache of the addresses and it can do least recently used, and that's going to work. And well, the guys at Nanog, they just ate that for some reason, and in fact, enterprise networks ate that as well. Because for everything we build, and Evpn is no exception, we are maintaining more and more state in the network. So the desire on one direction is what the Android guys will tell you. They don't want to support the DHCP. They just want to be able to use and claim any address they want. And if anything goes wrong, it's the fault of the network. It's never the fault of the user asking too many addresses or doing wrong things with its address. Always the fault of the network. The master is the device. Well, when you're a network operator, corporate network admin or what, it's not what you want. You basically want at least some control on the addresses, because at some point, you may be asked who is behind this address. You may be you may be forced to provide some services for which you have to deploy resources associated to these addresses. So just to be able to have the proper resources deployed to face the need of the network, you need to be able to have some control on it. Say, hey, you can't have more addresses than that. You're already using too much of them. Or who's this guy behind this address? Can I trust that it's not somebody stealing this address. And guess what? With stateless address auto configuration, it's very, very easy to steal an address and just claim it and start getting the traffic. The bottom line is the way this reactive protocol operates is completely non-deterministic. The network cannot build a clear view on which addresses are present on the network, which devices on which address. You don't necessarily know when it's formed, and you definitely don't know when it stops being used. And this is the major cause of broadcast unknown and multicast traffic in the network, because basically this cache-based reactive operation forces the network to look up anything that's not known. So yeah, auto configuration could be very fine, having the devices. For instance, if you think of this cluster of servers and the DevOps deploying stuff, they really might like to have autoconf, like the device suggests which address and prefix going to use. And as long as it's doable on the network, yes, the network could say yes. But on the other hand, there should be a way to say no. And there must be a way to make sure that you know exactly deterministically which address is where in your network. Next slide, please. So this slide basically summarizes the kind of issues you get with Slack. Slack doesn't tell you when there is a movement. Slack does not tell you how long you're going to use the address. The only thing you can do for Slack is snoop the DAD, basically, and the ND protocol. And that's very unreliable because it's based on broadcast. And if you have some wireless environment, for instance, you might lose them, mislead them completely. And the lookup basically is the only way to find a silent node, which means that you will have a broadcast through your fabric, or you won't be able to serve that silent node. The whole concept of silent node is something that we don't want. We want to make sure we have a state for everything that's present on the network. And basically, Slack is a major cause for not knowing that. The result is the number of enterprise networks won't support Slack. They will only support Dhcp, and guess what? Android does the reverse. They only support Slack. So at the end of the day, you can't serve IPv6 Android devices on an enterprise network. Next slide, please. So yeah, I mean, that was the status 20 years ago. If you realize IPv6 is 25 years ago, IPv4 is 40 years ago, from the perspective of 2020, both are old protocols. The difference is IPv6 has evolved. It has evolved because of SRv6, it has evolved because of the IoT, not because of the mainstream IPv6, but it has evolved. And in particular, this concept of the bad aspect of the SL in Slack has been addressed. It's been addressed by RFC 8505, which basically is kind of a reverse Dhcp. It's the device does its protocol. It tells the network, hey, I want to use this address. And the network says yes or no. For many good reasons, like duplication. This takes IGMP off the picture. You don't need any broadcast, but for the array, if you like, but coming from the network, the device. But basically, you go all the IGMP, all the multicast operations which are related to the neighbor discovery, stateless operation, all this is gone. You've got a stateful, observable exchange between the device and the network. And based on that, we can effectively build a reliable, stateful, deterministic state to Evpn, because now we know exactly which IP addresses are present on which device. And RFC 89 basically is the security of it. Basically, making sure that somebody who claims the address wants to use the address is the owner if this address was already present in the network. So it's a kind of a proof of ownership based on auto-configured key as well. So it's all auto-configuration, you don't need PKI or what. But basically, when you claim for the first time an address to the network, you're associated with a token that you can prove later. So if you move, or you re-register the address, you can prove you're the same guy as did it before. Next slide, please.
Pascal, you have 2 minutes left.
Yeah, so that's I'll be good. This is basically the goal of this draft. It basically enables to use those RFC 8505 and 9228 in the context of Evpn. And so using the signaling that comes from the host, we'll have better tools for sorting out duplication from Anycast from movement. We have a sequence counter, for instance, that each time the device says, I'm here, I've got this address, and each time it moves, it will have to do that, and we can sequence that. We can know exactly what is the latest location of which address, which means that we can know where to inject it in Evpn. And we will carry with this draft, we carry as well the tokens that can prove the ownership. So if somebody goes on the other side of your Evpn network and says, I have this address, well, you can validate that. You can say, oh, yes, he does, or no, he does not. Next slide, please. So here is basically the flow that happens in that case. And because I'm short of time, I will leave that. But basically, you have to register every address with a lifetime and do that periodically. And when you move, you have to re-register it for the same location. Then we are signaling from Multicast and Anycast. Next slide. So here is in more detail how the neighbor discovery registration works for a host that does the security piece. So you see there is a challenge, a north exchange, and it's all based on a key pair that was auto-configured by the host. And that is used to generate a token that the network will keep. Next slide, please. So yeah, the draft has been stable for a while. We got a very good discussion by Yogi. So this is done. I mean, we are now ready for adoption if the group is interested in following up with this. A number of other protocols have already done that, and that includes Rift, that includes Revo. And we also have redistributed at 505 to RFC 8929, which is actually a neighbor discovery proxy. So you can interrupt classical neighbor discovery with 8505 using an ND proxy. So yes, I mean, at this point, I don't know what to do, but ask if you guys are interested for adopting this work. And that's it.
Thank you, Pascal. There are no questions. Okay, let's try to resume with Aibo.
Hello, can you hear me?
Yes.
Okay. Let me continue. This is our motivation. We want SPID is very useful for 3P scenario. It can save resources for one side of PE. But for IPv6 network, the discriminator for each PE must configure it manually. It may cause the process to be complex. According, there are also some extension for IDP to provide SPID discriminators, but it's not satisfy the inter-area or inter-domain scenario. Next slide, please. This is the first scenario that we want to resolve. This scenario is inter-domain, and the service will use SRv6-BE. It's a typical 3PE scenario. The user CE will single-homed to one access PE, and the service is multi-homed to two service PEs. The access PE will create a SPID instead of BFD session. Then they can save the resources of a service PE. Each access PE then will create a SPID session. The BFD session will be maybe very huge. Then the remote and each SPID session will use manually configure the remote discriminators. And for SRv6 service, we may use SPID session to detect remote SRv6 locator prefix rather than VPN seed. It also can receive resources. The next slide, please. This is another scenario. It's very similar to the previous one, but the service now will use SRv6 policy for the service. Next slide, please. This is our solution. In our solution, we want to reuse the BFD discriminator attribute, also defined in RFC 9026. They are the type 38 attribute. And we don't do any change to SBFD. In our solution, we are introduced two new BFD modes. The first one is SBFD for SRv6 locator session. The second one is the SBFD for common session. The first one, we will use it to detect SRv6 locator prefix. In this type, the optional TLV will contain source IP address. It indicates the remote remote P is SRv6 locator. But for the second type, the session will use to detect remote routes net hop. Also means the remote P is the tunnel endpoint. And in this TLV, it will contain the remote P is the next hop address. Next slide, please. This is the procedures for the reflector PE. The BGP VPN roles will advertise with their local discriminator carried in the BFD discriminator attributes, and the BFD mode will be set to one of the new modes we have defined before. But for initiator, the BFD model will use to create the SBFD session when we receive the remote P the discriminators. For type 1 mode, we will create the BFD session to detect the remote SRv6 locator prefix. And for type 2, we will use it to detect the remote endpoints. Next slide, please. Okay, and also we have we have received some comments in the mailing list, and we still welcome more comments and discussions. And also later we may revise our draft according to some discussion. Thanks.
Okay, thank you, Aibo. I don't see any
Okay, thank you.
on the queue. Okay, Eng, we will retry with you. Eng, we still don't hear you. Feng Ong, do you want to say something? Please unmute yourself. Okay, it's still not working. We are not able to hear you, Eng. So unfortunately, we will have again to move to the next speaker. So next speaker is Feng Ong, and if we have time at the end, we can retry again, Eng. Let me pop up the slides. Feng Ong, do you want to take over and present your slides? Please unmute yourself. You are on mute, Feng Ong. Okay, it seems that we have issues with both presenters. We can, Somia, do you want to take over and present your dampening back of slide?
Sure, yeah.
Okay, let me just pop up the slides. Okay, please go ahead.
Yeah, hello everyone. So I'm back here again. So this was a draft which we did again around half an year back because of the same reason we were not able to present. So I work with Aruba HP and my co-authors Vinayak and Swati also work there. Next slide, please. Next slide, please. Yeah, you can have this. Yeah. So the problem statement here is we have talked about MAC dampening in RFC 7432, which talks about the dampening counts and the timer and the MAC moves observed within that, right? That has already been talked through in detail, and there was some portion left to implementation per se, including how do we handle with the freezing of the MAC and how do we unfreeze it or defreeze it post unfreezing? Do we freeze it forever? Or there is an organic way to freeze, unfreeze, check it again, and go on. I mean, it's all left to implementation. But I want to sort of put forth thoughts here where we want to actually do something on that side as well, right? So the best option here would be to freeze it forever. But if no operator is taking care of it, right, when sort of it's frozen forever, it's down the drains, right? And there is no correction which is happening. Let's say the time is non-deterministic here, right? It would be okay to handle it in a organic way where we'll want control plane, I didn't say control plane, but extensions to control plane where we define certain ways of defreezing and again running MAC dampening on top of it as a complete solution. So this is what we have been trying to propose here in this draft. It can be more of information if not standardized per se. So again, as already discussed, the typical problems of MAC duplication or MAC moves per se, which leads to dampening our dual MAC configuration, sorry, the MAC configuration, the wrong configuration of MACs, and let's say two different VMs in a DC scenario, or let's say in campus per se, where there is a rogue device which is mimicking two Macs behind two VTEPs. So that's very possible. So another case is of the loopy access side client network, where you have the client side network where, let's say, the fabric operator has no hold. So it would lead to relearning of Macs at dynamically learning at two different VTEPs, and this can go on forever. The stickiness of the Mac will also not help because this loopy side network won't, I mean, help you converge, right? So that's where we are. Can you move to the next slide, please? Yeah. So what we intend to define here is something called a MAC freeze timer and a wrapper around MAC dampening timer, which was defined, and the MAC dampening counts, which were already defined in 7432, and have all of this under the same umbrella called a MAC dampening attribute set. And so essentially the aim here or the goal here is to get to the duplicity as soon as possible if the operator hasn't taken control of the situation. This may entail freezing the MAC for a longer duration than, let's say, an earlier iteration when MAC dampening happened and the MAC was frozen, right? Or uh, and a combination of two that would help us to elongate the freezing time and reduce the duplicity detection time or the MAC dampening timer here, along with the count in an organic way. where we can define the iteration. So we can define the complete package in one iteration and take it further. Can you move to the next slide, please? Yeah. So this is how it works. So we have these three values under an umbrella. When I say one iteration, it's an iteration of dampening detection and freezing, right? And unfreezing per se. So this whole bunch of procedures, or the two procedures, can be put under one iteration and can be tracked and cached instead of just going ahead and freezing the MAC, right? So essentially, as we see here in the slide, that the nth iteration of the MAC damping time can be little lesser as compared to the previous iteration. The counts can increase where we want to uh, have more number of counts within the same iteration, and also the freezing timer. The freeze timer can increase where we give ample opportunity or provide ample opportunity for the admin to take care of it, take care of this problem situation if not done in the within the earlier iteration. And this is how it proceeds. So yeah, this is the solution. And next slide, please. So with respect to time, NFT, the freeze timer, it increases till infinity. So eventually you are going towards a complete freeze, but in an organic way. You are going up the blip and showing up and then freezing again. Whereas the dampening timer is shortening enough to going to zero. So eventually we want both of these to converge where it leads to a complete freeze of MAC if these intermediate stages or iterations of the whole solution doesn't work. Yeah. Next slide, please. So this is a sample example of the Duke Mac, and I have given few examples wherein how the timer values and the count values can be dealt with, and even the deltas by which these variables are addressed, those also can be addressed, those also can alter within each iteration. So yeah, please go through these details in the draft and let me know your views on this. Yeah. Next slide, please. Right. And backward compatibility, since all this is restricted to one device and there is no control plane exchange, I mean, except the extended community max CPS number, which leads to this dampening, or which helps derives the dampening state. There is nothing much which is exchanged. All this is under the purview of the same uh, uh, device. Yeah. Next slide, please. I think we are done here. So
Yeah,
I
this is
need, yeah, yeah.
okay.
So
Any question?
any,
Luc, go ahead.
It's just a general comment. Sonia is on this slide. If there's no control plane exchange of the values, I think the feedback would be why do we need to standardize this?
sorry, I'm not able to hear completely. Can you repeat again, please? Can you
If
repeat your question
the
again?
question was if there's no control plane exchange of the values, this seems to be very implementation dependent, which is where 7432 had explicitly left it off on purpose. So maybe that was really the only feedback is if two Ps don't need to communicate this value, maybe expand on the benefit of standardizing it.
But still, we have to have procedures, right? Which can be information per se, can help converge onto how we deal with this situation.
Okay. Jorge?
Yeah, hi. I had similar comments to what Luke was trying to say. Since you are not changing the control plane change, or you're not adding any changes in the signaling, at least the draft should be informational, in my opinion, not standards track.
Sure, John. Yeah, I wanted to do that, but probably I missed it in the thick of, yeah, in the flux of things. I'll do that. Yeah.
Thank you, Samia.
Thank
Okay,
you.
Eng, we can probably try again for last time. Yeah, please unmute yourself. Yeah, Feng Ong, can you speak? We are not able to hear you now.
Hello, can you hear me?
Yeah, yes, it's working well. So which draft do you want to present? Is it the upstream DF selection, or do you want to go through the other one?
So,
Yeah, sorry, Feng Ong, but it seems that there is some issue with your audio. Do you want to try again?
hello. 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 Can you hear me?
Yes, try again. Okay, so go ahead with the presentation. Feng Ong, do you want to start the presentation?
Hello, can you hear me?
Yes. We can hear you. Hello? It seems that you are not able to hear us.
Hello, can you hear me?
Yes, yes, we can hear you. Okay, if you are not able to fix your audio, you may probably have to close the session.
Okay. Okay. Here is Heng Wang from Huawei. Okay. Hello, everyone. Here is Heng Wang from Huawei. This presentation is about the VPN fast failover improvement for some use cases. Next slide, please. As we know, RFC 9826 has defined UMH selection based on P-tunnel status for VPN fast failover. The main procedures include first, determining the status of a P-tunnel. Second, the standby simulcast routing, advertising with a new standby X community. And the third, the hot route standby mechanism. However, in some cases, judging the status of a P-tunnel could be somewhat complicated. For example, the multicast flow is discontinuous for sampling, or the devices may not have the BFD capabilities. On the other hand, hot route standby may result in the steady traffic redundancy throughout the backbone network. Therefore, we propose an idea that the upstream PEs may make more efforts for the fast failover. They may perform a designated forwarder selection to prevent the traffic redundancy in the P-tunnels. And consequently, the downstream PEs may perform an Anycast RPF checking to accept any of the flows from the candidate upstream. The upstream DF status described here is per VRF and could be more refined for further improvement. So here are some details. Next slide, please. Upstream designated forwarder selection, we hope to use some existing methods to perform the DF selection. Take VRRP, for example, as shown. The roles of the VRRP routers can be mapped to the VPN dual-homing upstream PEs. Both the primary and standby PEs install VRF team state from BGP simulcast routes and send join to customer source direction. When traffic arrives at both upstream PEs, only the primary one forwards the flow into P-tunnel to downstream. The VRRP is just one technology. Other private implementations would be optional. Okay, next slide, please. We consider a new extended community called Upstream Forwarder Selection Community. It is an IP address specific X community carried on BGP VPN routes of unicast or multicast address family. The global admin field should be set as an identical virtual IP address, such as VRP virtual IP, or similar identity for other technologies. The local admin field should be set as the master or backup status derived from the DF selection. The main usage of this community is to inform downstream PEs the upstream behaviors and make downstream PEs to execute an Anycast RPF checking. Next slide, please. Downstream PEs still need to advertise a standby simulcast route described in RFC 9026. However, the standby PE community is no longer necessary. Of course, the upstream PEs can decide their primary or standby roles by themselves. Downstream PEs then accept the seed flow from any of candidate upstream PEs and forward it to CE. It's a kind of Anycast RBF checking. As a result, the seed flow duplication in backbone will be prevented by upstream PE CF selection, but not downstream, as mentioned above. Okay, final slide, please. Next steps. We are going to specify more details for more failure scenarios to provide per leaf or even per flow DF status. Seek for comments and discussions. Sorry, my speaker is it's a little bit. I can't hear what you say. So if you have any questions, please put this comment in the mail list, and we can discuss that later for details. Thank you.
Okay, thank you. We are already out of time, so we don't have time for the last presentation. So thank you, everyone, for your attendance, and hopefully we can see each other at the next IETF. Thanks, everyone.
Thank you.
Bye. And thank you, Jorge.
Thanks. The only two survivors.